Okay, now we are recording. We had already started, but we didn't get too far, so it should be okay. Going through announcements. So as pointing out, the video collection's almost complete, and you can use these to prep future labs. We'll add the lab 9 one down here, which is new, and I'm excited about and nervous about because we haven't tried it yet, but we're going to go through it today, and my students will be trialing it next week. The capstone that I've been long promising for this sequence. Anyway, the collection of videos is almost complete, and I'll upload this one after the meeting. Other announcements, if you're doing Lab 7, I know some of you are. In Lab 7, each student takes a dozen 2-second radio spectra. And we've been having a lot of difficulty getting these through our currently only one radio telescope. There used to be 1-second spectra, and that just, we had a hard time getting them through. It's something with the back-end processing. If the observation's too short, it freezes the whole system up. So we changed it to 2 seconds, and things were much better. Though over the past year, they've made some further changes, improvements to the code, and now the 2-second observations seem to shut down the system like every 5th or 10th observation. And on the optical side, we have linking, where if you have a bunch of students submitting the exact same thing, it just observes it once. We don't have that on the radio side. We will in Skynet 2, but until then, it means every student across the whole nation who's doing the curriculum are submitting 12, and so the telescope's flooded with these. And every 10 we have to shut down and if the operator doesn't notice it, it sits until I email the operator. It's the operator, the Green Bank telescope, but also their job's to keep an eye on the 20 meter, and then we reboot it. So it's taking a very long time to get through these. I've already changed it to 10 seconds in the video, and I uploaded the new video, and I changed it to 10 seconds in the text. But I can't change the text of the Cengage product. It has to go through their revision cycle. So that part won't be updated until next semester. But we'll try 10 seconds. And although it will eat a ton of telescope time, hopefully we'll have Skynet 2 almost done. And in future semesters after the spring semester, the longer exposure time won't be a problem. So trying to adapt to that, and it's not supposed to jam. And we are building all these new radio backends in Australia. We have someone in Tasmania working through the code. He's aware of this, and he will try to fix it in the code anyway. Anyway, if you're stuck on this, if you're doing this lab and your students aren't getting observations back, email me, and I'll send you a list of 12 good ones they can use as we work through this technical difficulty. Let's see, what else? We were just mentioning earlier this week, I sent out every semester I send out one of these, reminding you to do your end of semester surveys and to sign up for the next semester. If you're not offering OPIS this time, it doesn't matter, but if you are offering OPIS and you did the pre-semester surveys, it's really important to get the post-semester surveys. They're really only useful if we get students who do both. And there'll be some fraction that do one, some fraction that do the other, but not the one. Often at the beginning of semesters, the students are full of energy and enthusiasm, and it's not too hard to get them to do these surveys. But by the end of the semesters, everyone's tired. The instructors, we are tired. And so this is just one more thing that we have to do. But this is what the NSF funding's for. And you're all, getting $500 every time. If you offer it any time during the year, you get $500, and the $500 is for the surveys. And there's additional money for the training that you're doing now, and eventually a feedback session. But try really hard to get a high response rate. We give you some hints. Here are the links to the new surveys. Don't use the links to the old surveys. The pre's and the posts, we use different links. The pre should be closed down. They shouldn't even work now. I provided some sample text that you may want to share with your students. There's an encouragement video here done by Rachel Freed, my education postdoc. I imagine they're tired of watching videos of me at this point, so I got her to film this one, different perspective, and it's short. And you can offer extra credit and do whatever you can to get a high throughput, and that's greatly appreciated. Okay. And I have one more announcement before I dive into Lab 9 stuff. We got our first learning gain results. So far, the education research team is focused on self-efficacy. Our postdoc, Rachel Freed, she did her PhD thesis on creating self-efficacy instruments in astronomy and STEM. And so we focused on that first. It became part of her thesis. And as I think I've mentioned before, the self-efficacy results are just astronomically, shockingly good. Effect sizes between 1.5 and 2, which is nearly unheard of. And so it's being published in leading education research journals. We weren't hoping for that level of success with the learning gains, but we still would like a decent learning gain result. It's been slow to process because every school does a different collection of labs. So we had to change our coding in the SAS software that they use to average only over the labs that each institution did. And so they've now got that code working. Here it is processed for spring 2022. So a couple springs ago. And we process all the schools, but some schools have very small numbers. These are just the plots for the ones with at least 30. But the study of all of them together is representative. And these are pre-results. These are post-results. This is the OPIS Content Knowledge Survey, which I wrote, but David McKinnon, schooled me on writing a good one. My first one was rejected and sent back to the author. And there are certain tricks to writing these such that you don't clue the students in. Like all the possible selections have to be about the same length. If there's one that's much longer, that's usually the correct one, and students jump towards it, etc. Anyway, here are the effect sizes that we got for the 5 biggest institutions that semester, and they're hovering around 0.8, which is anything bigger than 0.5 is moderate, bigger than 0.8 is large. So we're in the moderate to large range, which is very good. Very happy about that. Normally, if you get more than a moderate result, you're jumping up and down that you're doing something right. So, this curriculum was designed to boost self-efficacy. Yes, I can do this. Content knowledge, we, of course, wanted a good content knowledge result, but it wasn't the primary thing. But it's nice to know that we're being very successful in that regime as well. We haven't yet done the gender breakdown like we did with self-efficacy, where in the self-efficacy result, there's a gap between guys and girls that disappears by the end. And that's also a very exciting result. This is very early days for the content knowledge study, but promising, very promising. They are learning the lessons. Okay, I'll just pause. Any questions about anything? Your own implementations, anything before we dive into Lab 9?
I had a really quick question from a student last night.
Okay.
I just want to confirm that even though WebAssign has a close date, if they have time left in Skynet, their accounts don't automatically erase them. Can they
That's
continue?
right.
They want
Yep.
to keep playing.
Yep. So Skynet and WebAssign, totally separate entities. WebAssign is Cengage, and we, third-party partnership, and Skynet is internal, and that's why there are 2 signups, right? The time will remain probably for about 2 years, and then we clear out the old accounts.
Great.
In the past, we've had educators that would pull the extra time and start doing research with it, and that wasn't really the intent. It's there for the students, and there's enough time for them to play. But yeah, if you want to do research with Skynet, I'm happy to sell you research time.
Right.
Yeah,
Yeah. No, this was totally the students who wanted to keep playing with it.
and that's great. That's great that they're so excited
Yes.
and want to keep doing their homework even after the class ends. And so that's a great sign.
I
And
have a related question. I know that for WebAssign, the access is limited. Can I still have access to it over the winter break? So I'm a little behind, so I can
yes,
catch up.
the course is closed down, but with your instructor account, you go to previous offerings. They when you log on, you just see your current offerings, and so you won't see it after the close date. Go to previous offerings, and it will be there. And if you have any
I think
problem,
I'm a TA. I think
okay,
I'm a TA in one of the, yeah. I have to,
TAs get instructor accounts, so it should still work just the same.
all right, perfect.
Cool. All right, Lab 9, long awaited, long promised. This has been a long journey to come up with a capstone. It's meant to be a capstone for labs 5, 6, 7, and 8. In 5, they learn how to use standard candles. In 6, they use standard candles to do the Great Debate of 1920, specifically the R-Lyries.
Question.
Yeah, please.
What is capstone mean? This is a new word to me. Sorry.
Oh, okay. Capstone is like a final effort that pulls together lots of things they learned from the previous efforts.
Okay, great.
Yeah.
Thanks.
And right. And so in lab 5, they learn how to use standard candles. Lab 6, they practice using them to do the Great Debate of 1920. In lab 7, they learn how to collect radio spectra, which is a skill that we're going to use again. In lab 8, they learn the true nature of the expansion, and that's the rubber band lab. So it's not a Skynet data lab, but hopefully it gets to the heart of what's really going on and cures them of their misconceptions, that it's not a boom in the middle of empty space, but everything's uniform from the beginning and space is expanding, pulling apart. And so the capstone has always been, they're going to measure Hubble's constant. It's at the very cap of the cosmic distance ladder. And so if they measure it, then you're measuring the rate of expansion of the universe. You're also measuring the age of the universe. The inverse of Hubble's constant is the age. Now, I'll give you a little bit of backstory because it also kind of introduces you to some MWU stuff. The problem was, if you're taking the cosmic distance ladder approach, you need a redshift and you need a distance. Basically, C times the redshift divided by the luminosity distance is Hubble's constant. No, that is in the local universe. So you need a redshift and you need a distance. And I really want them to measure one of these things. I don't want to just give them numbers. At least for one of them, I want them to measure something. And traditionally, the redshift comes from optical spectra, and we don't have any optical spectrographs on Skynet. And the first ones we will have will be low resolution, and you won't get a good redshift. So I've been trying to figure out what to do. The plan for the longest time was to use gravitational wave events, which are new and exciting and will eventually be a new way of measuring Hubble's constant in the local universe. So we have something to compare against the cosmic distance ladder technique, parallax Cepheids type 1As. They've given out Nobel Prizes for. And so the idea was we're going to use the gravitational event GW 170817, went off in 2017, August 17th. And it's, they've detected lots of merging black holes, and something you can't see merge with something you can't see makes something you can't see. And you can't get a spectrum of something you can't see. But for this one, there was 2 merging neutron stars, and it produced a gamma ray burst and a kilonova. And we could figure out what galaxy it's coming from and get a spectrum. So the idea was we'll just give them the spectrum of the galaxy, but they'll measure the distance by modeling the gravitational wave event. We spent a lot of time figuring out how to do this, and it's mostly done. There's still a few bells and whistles to add here. We decided not to use this in OPIS. This became an MWU activity for reasons you'll see. I figured I'd just show it to you. You can go to it links directly to the LIGO site, and you have all their events. Let's go back down to the beginning here, their first big one. I haven't showed this to you before, have I? The gravitational wave tool. Okay, so just a fun little preview of MWU stuff. And so this is what LIGO provides. This is the frequency and this is time. So as those either black holes or in this case, two black holes getting closer together, they spin faster and faster, and the gravitational wave signature gets stronger and stronger. Here's a nice one here. LIGO has two detectors. And you see, it's only strong enough to make a detectable signature over the final few tenths of a second. Well, you can grab the 16 kilohertz data, download it onto your machine, and upload it into this tool. It takes about 2 minutes to process because we are actually using the LIGO source code, and it's very complicated stuff to turn the, LIGO is an interferometer, and as the waves go by, one leg gets longer and the other shorter, and vice versa. And they're measuring this ratio between the two legs of the interferometer. That's what the strain is. And so here they plot the frequency, and here's time, and here they plot the strain of the detector versus time. And so we can load in any event, which is kind of cool. And then you model it. It depends on the merger time, the total mass, the mass ratio, the distance. And so here, this is the first strong black hole merger that they got back in 2015. And so the interface is a little too sensitive for my taste. We still have a little bit of tweaking to do there. So I got the merger time. The total mass appears to be around 70. The mass ratio kind of changes the shape of it. I'm just fitting to the spectrogram right now. And then you do some fine tweaking down below. And we have a good merger model here. And the last thing we do is we adjust the distance. The farther away, the orange is the model and the purple is the data. And so you can adjust the distance till you get a decent representation of the data. So you can measure the distance to these events. It's actually independent of the whole cosmic distance ladder, parallax, Cepheids, type 1As. It's going to be a great check for the Hubble tension problem that we'll come back to. So we built this tool, and pretty cool. Now the students can just grab the professional LIGO data and make their own analyses. But it didn't really work for the capstone. The reason why is the one event where we do have a redshift, an honest to goodness redshift, the 2017 event, it was sub-noise. So the noise in the data, you can see it on the spectrogram, the top panel, but the noise in the data down here, it's too much. And the model is below the noise. And so you can't fit the distance. And that's what we needed to get Hubble's constant. So we built a lot of stuff, and we didn't throw it away. This is a whole module in MWU. I have a group building a curriculum around it where you do approximations with Kepler's third and see how the general relativistic is different, and it ties into the Hulse-Taylor pulsar, which is a coalescing system that still has hundreds of millions of years to go. So we're happy with the tool. We're happy with the curriculum that's being developed for MWU, but it wasn't what we needed for the OPIS capstone. Now, as we were doing MWU in module 6, we're now on to this is module 5C. In module 6, we get on to galaxies, and we weigh galaxies, and we do it by looking at the hydrogen line in the radio. Just like in OPIS Lab 7, they're taking spectra and seeing the hydrogen line in the Milky Way galaxy. You can also see that same hydrogen line in nearby spiral galaxies. It's much, much fainter. So you have to do a slightly different type of spectral observation. But we learned that you can do this. And there's about 5 galaxies that you can detect the hydrogen line with 60 seconds on, 60 seconds off. In Lab 7, it's 2, and I now said 10 seconds straight up. But to bring out the fainter line, you don't just do a straight up spectrum. You do something called an on-off spectrum. I'll show you how to do it. And we limited it to things that they can do in 2 minutes, 60 seconds on, 60 seconds off. There's 7 of those galaxies. 2 of them are in the Virgo cluster. So the redshifts you get for those are mostly dominated by them being pulled on by other galaxies in the cluster, but the other 5 are not gravitationally coupled to stuff. And so we have 5 good galaxies, and I'll just kind of spoil the end result. All of them give Hubble's constants between 60 in the 60s and 70s, just from a single galaxy. And so I was pretty excited about that. And then at that point, I realized that's how we're going to end OPIS. So just to review, the capstone for OPIS, they're going to get the redshift from a radio spectrum. And for the distance, we'll give them a Cepheid, just like we did in Lab 6. So one observation, one thing given. They have the redshift, the distance, they have Hubble's constant, they have the age of the universe. And we also decided to throw in measuring Hubble's constant from the CMB. And you're probably aware of the Hubble tension, that the CMB and the cosmic distance ladder give slightly different, but statistically different results. And so this lab is kind of builds up to the Hubble tension. Okay, so we're going to go through it now. Right, it doesn't exist in WebAssign yet. I just finished writing it a couple days ago, and in fact, I made a few more edits this morning. But they're in Word documents. We have 3 documents here. We have this one here, which you can use with your students. I decided to double this figure and add a few more links just this morning. But the copies I sent around a couple hours ago, perfectly good. And there are places where the students can write in their answer. So if you do decide to do this semester, you basically print these out and hand them out, and they will write things by hand and hand them back and doing manual grading. But hopefully by next semester, Cengage has this all coded up. So there's that version. I have a version here with the solutions built in, little comments on the side, like down here. And these are the solutions that Cengage will code into the auto grading. And there's also a sheet that has sample calculations. And we're trying to build these into all the labs. Labs 1 and 2 have them so far. The others don't yet, but these are the sample calculations for Lab 9. We realized one of the remaining things students struggle most with are the calculations. So by providing examples, we hope to make it that easier for them. Let me see if there's anything else here. Nope, now I'm just going to go through. It says my internet was unstable, but I guess I'm back. Let's just go through Lab 9, unless there are any questions, comments. Okay, we'll do this now. So the goals of the lab, as I just described, they're going to do radio spectroscopy of nearby spirals, a nearby spiral. Each student will pick one. To get a cosmological redshift, we'll give them a Cepheid in that star, in that galaxy. To get the luminosity distance, they'll combine these to get Hubble's constant. And they'll learn how to measure Hubble's constant in a completely different way using the CMB. And then they'll learn how to turn those measurements into ages, pretty much by inverting Hubble's constant. So a couple background sections. I know you know most of the stuff, but I'm just going to run through it kind of quickly like you would with the student. This is kind of a review from stuff they learned in the previous lab, Lab 8, that, once we look out beyond, with Andromeda and closer, we're gravitationally coupled. But once you go beyond Andromeda, the farther out you go, the galaxies appear to be moving faster and faster. And as they learn with the rubber band exercises, this is not due to motion through space, it's due to the expansion of space. There's a little review diagram of that. Mathematically, it's given by Hubble's law. So CZ is HDL, where C is speed of light, Z is cosmological redshift, H is Hubble's constant, and D is the luminosity distance. CZ, the combination, is how fast the galaxy appears to be receding. Appears, because remember, it's not moving through space. The space is expanding. Where Z is just a fraction of the speed of light, or if really far away, how many times the speed of light the galaxy appears to be moving. And we measure that in kilometers per second. And this is building up to the strange unit. They need to understand the strange unit of Hubble's constant. And then on this side, luminosity distance, we get this from looking at a standard candle. And in lab 5, they learned how to use Cepheids and type 1As. Except on these scales, we don't measure them in kiloparsecs, we measure them in megaparsecs. That's a difference from before. And so Hubble's constant is just the ratio of the two, CZ over D. And hence it's measured in the weird units, kilometers per second per megaparsec. It's really just telling you how fast in kilometers per second is each megaparsec of space stretching. That's what Hubble's constant gives you. And as I said, we measure Z from the galaxy's spectrum in the radio. They learned how to do that in lab 7, though there's a twist here since they're so faint, being farther away. And for the luminosity distance, we'll give them a standard candle in the galaxy like we did in lab 6. Okay, we'll do this in procedures A and B. So no surprises there. Now, if you want to do a short version of this, you can just do the cosmic distance ladder component. But the longer version, we also introduce them to the CMB. You often teach that in your courses, so it's nice to have a place to put it here in the lab. So I give a little bit more background here to try to explain what the CMB is and its characteristics, but again, very briefly, giving just the minimum of information. You're welcome to supplement. So the idea is space is expanding. So if you run the clock backwards, everything gets closer and closer together until it's no longer distinct galaxies and stars. Everything's mixed together in a hot, dense gas. And if you go far enough back, the gas is dense enough that it's opaque. And opaque gases produce a black body spectrum. But since it's opaque, this black body spectrum, it's emitting the black body spectrum, but immediately reabsorbing it because it's opaque. But eventually, running the clock forward, the density drops. Eventually, it won't be opaque, and that thermal spectrum at that moment in time, whenever the universe becomes transparent, is then released from all points in space and in all directions. And in parentheses here, I have a technically what's going on is as the density drops, the temperature drops, eventually drops to a point where the protons and electrons combine up into atoms. That's recombination. And that is when the light escapes. So it's not just the density drops, there's a transition here, temperature-based transition. But it's in parentheses because it's kind of an extra. And, it's emitted from every point in space in every direction. So it should still be here at every point in space going in every direction, except that the wavelengths will continue to be cosmologically redshifted, stretched out by expanding universe. And we just referenced lab 7 because we taught them that there. And these cosmic background radiation photons are now stretched down to the microwave and radio part of the spectrum, hence the cosmic microwave background. And these are key predictions of the Big Bang theory, that if the Big Bang is as we described, there should be the CMB out there, and its spectrum should be that of a black body. So it's always nice to say, people think of the Big Bang theory as just some theory, but really it's a working model because there's so much evidence, and this is just the tip of the iceberg. We don't talk about nucleosynthesis here. There's so many lines of evidence. But anyway, key predictions. Is it there? Yes. Penzias and Wilson found it in 1967 using a big radio horn. And then by 1992, the Cody satellite measured the spectrum, and it is indeed a perfect black body. So 2 predictions of the Big Bang theory, 2 verifications. Okay, let's take it to the next level. Again, I know you know these things. I'm just summarizing. Next level. Well, it's a black body, almost perfectly uniform across the sky, but almost, not perfectly uniform. And this was also expected because after 380,000 years, the dark matter started to clump. And there's a little bit more detail down below, but it starts to clump. And in 380,000 years, there's not much time there. It clumps by about 1 part in 100,000. And this should have an imprint in the CMB. And, in that imprint should be variations in the CMB at the same level, about 1 part in 100,000. And indeed, the CMB is super uniform, but as we had better and better satellites, Kobe, WMAP, and then Planck in 92, 03, and 13. It got better and better and better. And these are the 1 in 100,000 part variations in the inferred temperature. So I mentioned here, this is our universe's baby picture. Before this, the light was coupled with the matter, nothing escaped. This is the first time light escaped from, decoupled and escaped from the matter. And so this is as far back as we can see, and we can see the beginnings of clumpings in the universe due to the dark matter. So then I answered just a few technical questions in parentheses. Why does the dark matter clump but not the normal matter? Well, the normal matter is too hot, feels all that pressure from all that heat, so it stays pretty uniform. But dark matter doesn't absorb that black body radiation, so it's been able to clump for that 380,000 years. And why does that result in temperature variations? Well, as the light is leaving the slightly overdense region, it gets gravitationally redshifted. And I don't go into great detail. I do a link if they want to study gravitational redshifting a little bit, or if you want to explain it more. But in the regions that have begun to clump, as the light escapes those regions, they're redshifted due to the greater gravity there. And this shifts the spectrum to the red, and so we interpret it as being a little bit cooler. So it's actually the blue spots in the CMB map that are the overdensities. The red spots are the underdensities, something people often don't get. Anyway, those are in parentheses because they're more like extra information. I felt I should answer them in case students have questions. But the simple story is after 380,000 years, you should get some clumping. You should see it in the CMB. It should be 1 part in 100,000, which is exactly what they saw. So yet another verification. Now, measuring Hubble's constant from the CMB is quite tricky. And I spent some time thinking about how can I simplify this down to the survey level. So this is what I came up with, and you can be your own judge. Clumping occurs on all scales, but there's a particular scale that's favored. And when they look at their CMB map, they'll see the clumps are almost all on the same scale, the small clumps. And this scale is set by how far pressure waves can travel in 380,000 years. As the dark matter started to clump, it set up pressure waves, and they could only go so far. So that sets kind of the primary clumping scale. Let's call that R. Now, that's their physical size. How big do they appear on the sky as an angle? Well, that's proportional to R over D, where D is the distance from us all the way back to the CMB. And according to Hubble's law, distance is quite simple. But Hubble's law really only applies in the local universe. To get the distance back to the CMB, it's a complicated equation, depends on omega matter, omega lambda, too complicated for survey students. And I say that here, this is just a local approximation, but even if you use the full expression, distance is still proportional to 1 over Hubble's constant. So what are the possibilities? If Hubble's constant is larger, D is smaller, that means the CMB is closer to us. So those R-sized clumps will appear bigger, something like this. Or if Hubble's constant is smaller, D is larger, the CMB is farther from us, and the clumps will appear smaller, something like this. And this is the size they do appear. So the size of the clumps in the CMB is directly proportional to Hubble's constant. Now, it does depend on all these other things, the physics of the pressure wave. In the literature, it's called the sound wave, but I don't want to confuse the students, so I just called it pressure wave. Depends on cosmological parameters. But if you hold all that stuff fixed to best values, it's quite simple. Hubble's constant is 82.2 kilometers per second per megaparsec times the size of the clump in degrees. And that equation is good to about 8%. So it took a while to figure out how to do it with students at this level, but that's what I came up with. And so they'll have a very simple measurement. They're going to measure the size of a clump, and it gives them Hubble's constant through a different mechanism, and it's an opportunity to teach CMB. And here's the last bit of background, the age of the universe. Once you have Hubble's constant, you have an approximation for the age. Again, I point the students to the unit, kilometers per second per megaparsec. Hubble's constant's measuring how fast in kilometers per second each megaparsec of space is expanding. But since the beginning of time, each megaparsec of space expanded 1 megaparsec. And it did that in the age of the universe. So Hubble's constant is also given by, well, space is also expanding at a rate of 1 megaparsec per t, where t is the age of the universe by definition. So Hubble's constant is also given by 1 megaparsec per t per 1 megaparsec, or just 1 over t. Solving for t, the age of the universe, it's just 1 over Hubble's constant. So it's kind of a nice free extra. Of course, that's the average rate of expansion. And you have to do some unit simplification. You got to convert those megaparsecs into kilometers so they cancel out. You probably want to put seconds into billions of years. So there's some unit conversion, but really just inversion and unit conversion. Now, I point out that because in the last lab they learned the universe is accelerating, the universe is not expanding at a constant rate. So this was based on an average rate of expansion of 1 megaparsec per age of the universe. Early on, the universe was decelerating. So all the mass was close together, pulling on each other. Gravitational self-attraction was stronger because it was closer, and that worked against the expansion. And then, as they learned in Lab 8, it's now not decelerating, but accelerating due to dark energy, which we, again, have no idea what dark energy is. It is that which causes the acceleration. But it's accelerating. But overall, these effects kind of cancel out. Here's a figure. You can see a little bit of deceleration early on, some acceleration later on. But really, the overall slope does a pretty good job. Just inverting Hubble's constant, you get really close. Okay, those were the background sections. All good? Okay. Now on to the procedure. In procedure A, they're going to start by in procedure A, they're collecting their radio spectrum. So this is the observation part. Now in lab 7, they learned how to collect a spectrum to detect 21 centimeter emission from cold hydrogen gas in the Milky Way. Now we're going to try to detect it in another galaxy, but this is much farther away, and so the signature is fainter. For example, here is this is a galaxy that's not on their list because it's in the Virgo cluster. I took it out. But here I took a spectrum. You see the hydrogen line, but that's the hydrogen line of our Milky Way. We have to look through our Milky Way to see the distant galaxy. This little tiny bump here is the hydrogen from the distant galaxy. And that's going to be really easy for the students to miss. So what you do in something like this is you do an on minus off divided by off spectrum. This is 1 minute on target, and then you shift over 2 degrees and do it again. You get almost the exact same background response and hydrogen response because you're looking through the same spot on the Milky Way. But that tiny little bump from the galaxy is gone because it's no longer in the telescope's field of view. So then what you do is you subtract the two. See, the big thing here are these variations in the background. That's not astrophysical. That's just the instrument. The instrument has a response function. It changes over the course of the day. You have these huge variation, making it hard to see that little bump. So you take the on spectrum, you subtract the off spectrum, cancel out most of the variations, and then you also have to divide by the off spectrum to flatten it all out. And you get this. And we didn't perfectly cancel the Milky Way's hydrogen line. We didn't perfectly cancel the background oscillations, but mostly we did. And so that tiny little bump up here is now quite discernible. And you can get these things out to, well, depending on how long you want to observe, you can get quite a few galaxies in the nearby universe, get their hydrogen profile. And we point out a couple things. First of all, it's much broader than the Milky Way's. It's because with the Milky Way, we were just looking through one line of sight. But with this galaxy, we're looking at the whole galaxy. And one side of the galaxy is moving towards us, and so its hydrogen emissions blue shifted. The other side's moving away, it's red shifted. So it gets spread out. This side here is the blue shifted gas. That's the side of the galaxy rotating towards us. This side's the side rotating away. Sometimes you even get a dip in the middle. You get kind of a horn-shaped profile, Tully-Fisher horn-shaped profile with spirals. And sometimes you get a Gaussian blur if the motion's a little bit more disordered. But anyway, in MWU, we spent some time working with that width there to figure out how fast the galaxy is rotating and weigh the galaxy. But here, we just want that central frequency. So this is where they put in the observation. They pick a target, and we've learned if they get to pick their target, that makes them super happy. They love having that freedom, that choice, and they can click on the links and look at pictures and say, okay, I'm excited about this galaxy, and they pick it. And these are all the galaxies. They're strong enough and have a hydrogen emission line strong enough to see in a minute on, minute off that are not in the Virgo cluster. There's only 5 of them. But okay, and so how to do this, I'm just going to show you. So go to Skynet, radio observing, add a new observation. I'll pick one on the list. Let's see. NGC 253 is the first one on the list. Look for it. Okay, it added the coordinates. I can pop around the sky and see where it is. It'll be tonight. The sun's way over here, far away. So it added the coordinates. You want to make sure that you're at least 10 degrees from the sun, because this is a really faint signature. The sun can mess you up if you're too close. It starts bouncing off the support arms of the telescope, gets into the receiver. And you want to be 15 degrees above the horizon, because some of these are pretty low in the sky. So this particular one's observable for 5.5 hours. Save and continue. Same as before, you want to make sure you're in the high frequency mode with the same center and secondary frequency. Save and continue. Pick a time account if you have multiple. And instead of a tracking observation like they did in Lab 7 for a certain amount of time, they're now going to do an on-off. So 60 seconds on, then we're going to move 2 degrees in right ascension, nothing in declination, and then we'll do 60 seconds off. So that's the only difference. Save and continue, submit, gets in there. Let's look at, here's one I did of Messier 83. So when it comes back, they're going to want to check, make sure that the link's not broken. If the link's broken, they can resubmit. But here's another one of Messier 83, the one I just showed you. And you can see there's that profile. If I want, I can go to my list. I just put in NGC 253. Let me find one of those as an example. So here you see that has the Tully-Fisher shape. The hydrogen line is kind of close to it, but again, the center will be right there. So a skill they've already learned just with this minor twist. And I have little reminders here of the key things they don't want to forget. And then they'll indicate which galaxy they did. And once WebAssign has the auto grading, that's critical because it sets the auto grading for the rest of the lab. Okay, 2 sections left, one cosmic distance ladder, one CMB. So now we're going to measure Hubble's constant and the age of the universe with the cosmic distance ladder. First, we're going to do the redshift, then the luminosity distance, and then Hubble's constant and the age. So in redshift, they start by measuring the central frequency. And as you go to this page, there's links down here. Like here's the on spectrum. Barely see the line there. Here's the off spectrum. But then here's the on minus off over off. And it looks to be around 1419 for this particular one. But if you go to live spectrum, and it takes sometimes a minute to load, and you click on the little magnifier and zoom in, then you can get a measurement to like a tenth. Like I'd say this is 1419.2. Okay. And a couple notes, we tell them don't measure the Milky Way line. It's the narrow one, measure the galaxy line. And also this is in frequency. In lab 7, we're in wavelength. This is in frequency because this particular tool is in frequency. They put their central frequency here, then they calculate the redshift. We convert the equation from wavelength to frequency. So just there, the emitted frequency is 1420.4 minus the observed divided by the observed is the redshift. And they put that here to 5 decimal places and show their work. Again, we have examples of all these calculations in the calculation document, redshift and everything they'll need. Then they do the luminosity distance. For each galaxy, we give them a Cepheid. And just like in lab 6, I'm pretty sure lab 6, we just made up the Cepheids. With these galaxies, particularly these right here, they're so close. The distances are actually not measured via the Cepheid technique. They use tip of the red giant branch and planetary nebula luminosity function, other things that we didn't teach in this lab. There are tons of distance measures. We taught the primary ones, Cepheids, type 1, parallax Cepheids type 1a, the cosmic distance ladder. And so these are just made up Cepheids, but they're made up to give the best measured distance by all the various techniques put together. You got to go farther out to rely more on Cepheids. In the very nearby universe, you have other techniques, and that's too much complexity, so we simplify it here. Give them a Cepheid period, they calculate the absolute magnitude. Give them the average apparent magnitude, and they calculate the distance. And here we give them the distance equation again, but now in megaparsecs instead of kiloparsecs. And so they're going to have absolute mag, they're going to have the distance, they already have the redshift. And so they combine the redshift and the distance and the speed of light, and they get Hubble's constant. And they'll get something between like mid-60s and mid-70s. It's actually really good for these 5 galaxies. We give them the best professionally determined value. The professionals use all available galaxies and both Cepheids and type 1As and all of that are available, and they get 73.4. And so they do a % error calculation and discuss sources of error. Sources of error, they only use one galaxy. Its redshift can be contaminated by Doppler motions due to other galaxies pulling on it. They only used one Cepheid when there are probably multiple in most galaxies, and also there are variations from Cepheid to Cepheid. Variations in the absolute magnitude. So all these things are possible sources of error. Then they calculate the age of the universe by inverting it and converting from the megaparsecs. You figure out how many kilometers in megaparsecs, so you can cancel out the megaparsecs per kilometer and how many seconds are in a billion years. And we give them examples in the calculation document where they invert it and then do these unit conversions and get the answer in billions of years and show their work. Given professionally best determined value, 13.8, they'll calculate % error. And additional sources of error is the universe wasn't expanding at a constant rate, it had some deceleration, had some acceleration, so this is just approximation. All good on the cosmic distance ladder part? Okay. Now the Hubble constant part. We tell them to go to Afterglow, and we've added in the sample directory. You can go into here and go into the sample space and Astro 101 lab, and there's Hubble's law, and now there's a new file they can upload, and it's this. It's the Planck map. And when they load, it loads on the first tab, and so it tells them to click on the color combination layer. And in the lab, we tell them to zoom in and find the scale, the typical scale of which things are clumping. And if you play with it, there is a pretty obvious scale. If I go, they're going to measure it using the measuring tool here. But the clumps are all I mean, there are clumps of clumps on different scales, but you've seen the I didn't include the CMB power spectrum. I thought that was too advanced for survey students. But just in here, whether you're measuring the red spots or the blue spots, there's a typical scale that really stands out. So we tell them to find a typical blob and measure it. And this can be fairly crude because do you measure the full width half max or from where to where, but it's good enough for this exercise. So they measure a clump in pixels, and for that particular image, each pixel is 0.21 degrees, so they convert to degrees, and then they calculate Hubble's constant, which is again just 82.2 times their size in degrees. Show their work, and then the best determined value using not just a single clump, but careful statistical analysis of all the clumping on the whole map. You get 67.4, so they calculate a percent error. Turn this into the age of the universe in the same way, in percent error. And lastly, we point out, I'll just kind of read it here, your two measurements of Hubble's constant should be consistent with each other given the very large uncertainties. But you probably noticed that the professionally best determined values also differed. The cosmic distance ladder gave 73.4, and here I include the error bars. I didn't include the error bars above because I figured that would confuse them as they're calculating percent errors. But 73.4 plus or minus 1.1, and the CMB technique gives 67.4 plus or minus 0.5. And although these are probably closer together than their two measures, particularly their CMB measure, I wouldn't be surprised if they get 80, 90, if they overestimate it a little bit. These two numbers disagree pretty significantly given their small error bars. This is called the Hubble tension. It's currently a hot topic in astronomy. Research the Hubble tension and describe possible explanations. And in the solution, I gave them a link to Hubble tension on Wikipedia. But in short, there could be systematic errors that are just not yet known for either technique. The simplest one to point to is with the cosmic distance ladder, perhaps type 1a supernovae, their properties change over time in a way that hasn't been accounted for. Or maybe we live in a giant void, in which case our part of the universe would be expanding a little faster, but it'd have to be a really big void, like bothersomely big, kind of violating homogeneity and isotropy at some level. Or perhaps, and most excitingly, there's new physics we just don't understand, and this is giving us a hint that can maybe teach us more about physics. Those are kind of the three basic explanations that are thrown about, but you know, it's an active area in astronomy. I just touch on it very briefly here, but if you're giving lectures and things on cosmology, you'll probably talk about the Hubble tension a bit more. That's the whole lab. Questions, comments? Wow.
It's more of a general question, Dan. I like having the sample calculations that you were showing. Is there anything like that exists for the existing labs?
I'm adding them as I go through and do updates. So labs 1 and 2 have links to sample calculations in them. The rest will as I update each.
Okay.
It's a slow process because MWU has taken over. You know, I was supposed to do all these updates like 3 years ago after I got my round of feedback and just crank them out. But I'm managing a couple labs this semester.
Yeah, no problem. I just kind of wanted to know because I had some students asking about it. So I was helping some students yesterday doing some makeup labs, and they were struggling with the math, actually, not the, it was actually the math part that they were struggling with rather than the
So it's
Skynet or Afterglow.
piece by piece, you know, over the next couple offerings, I expect that stuff to finish fleshing out. It's work in progress. So let's see, I have a few final, any other questions, comments? Okay, a few final notes here. Again, if you're doing the labs, please do those post surveys and don't forget your spring sign up so I can reserve the telescope time. The next note I have here is once you've offered OPIS once, you're more than welcome to join the MWU educator group. I've described it before. It's a big, happy community. They're currently broken into 3 groups doing different things. And in the spring, they're going to actually start going through the MWU kind of a training. Everyone worked on little bits and pieces, but we're kind of training everyone on all the modules. And if that's something that interests you, in case you want to offer some MWU modules, perhaps as part of your course, but perhaps as part of a different course. It's a very exciting curriculum. It's orthogonal in many ways. Astrophotography is the hook. It's more about star evolution, galaxy evolution, some planetary stuff as well. We're excited about the curriculum. It's like taking our ORIRA experience and embedding it in the classroom is the goal. Still in development, but we have stuff, and and it pays. If you were to join in the spring, there'd be $2,000 for you. $1,000 for spring, $1,000 for summer, and then the grant's over. So I hope to get more money in the future, but that's it for the current funding. And I'll send a scheduling poll around in a few weeks. You don't have to participate in all 3 groups. Any one is fine. And then the last thing is we're going to be holding a meeting, and I think I may have mentioned before, a meeting in Chapel Hill. It's not going to be in May. I have to move it. I'm trying to get inexpensive campus housing to make it really accessible to lots of people to come. And that doesn't become available until after the dates I've reserved. So I'm quickly trying to move things around. It'll probably be early June. And it's called New Technologies and Dangerous Questions in Astronomy Education. And it should not be your standard conference meeting. It should be pretty exciting and fun. But I just wanted to mention that and be on the lookout. I'll send an email about that as soon as I have the final bits and pieces scheduled. Otherwise, it's noon, and this brings us to the end of our semester training. I hope it was helpful and useful. Well, helpful, useful, same thing. I hope it was helpful / useful to you.
Thanks very
Thank
much,
you.
Dan. It has been.
Yeah.
Sure.
Yeah,
Appreciate it,
thanks.
Thanks.
My pleasure. I'll
We'll
stick
keep in touch.
around for a while because I'm waiting for my TAs. So if anyone has anything else, I'm here. Otherwise, see you soon.
Wow.
So Dan, for the Milky Way University stuff in the spring, the working group, you said you'd send some stuff around about that.
Yeah, multi-wavelength universe. That's what it
Oh,
stands.
sorry.
Yep.
Multi-wavelength universe.
Yep.
Sorry.
And
For some reason, it's stuck at Milky Way University in my brain. I don't.
Yeah.
Was thinking that,
Yeah, multi-wavelength universe.
Oh.
I will send probably in a few weeks. I'll send around when to meet poll and get everyone's schedules, and then I'll announce the times for the 3 working groups. One will be going through the radio modules, one will be going through the optical modules, and one is doing advanced work for the next big grant, which is kind of a majors level curriculum where they're going to be digging deeper. It's going to be an Argus based curriculum largely.
Oh, interesting. Yeah.
Yeah, and so we're going to ride this Argus wave as far as we can. And I'm meeting with Nick on Friday about initial ideas, but deeper studies of things like our Lyraes and exoplanet transits and cataclysmic things like supernovae and kilonovae and maybe some asteroid stuff, and where they will mine the Argus data set and other available data sets. It won't be so much about acquiring their own data, but archival mining and modeling. And not just like, oh, here's the period of this one next, here's the period of this one next, but like with our Lyraes, the periods, there are different period modes called Blazhko effect, and we're going to really get into it to a level where each object is different, and we're going to create catalogs and student level automated journals they can publish in their findings.
Awesome. Yeah, this is interesting because we've started the concentration for physics majors
Mm-hmm.
And we have a small physics department. It's physics and engineering science, right? So obviously there's a lot of engineers, but we picked up we had just a few physics majors. Now we picked up 5 new ones just because we have an astronomy concentration. So that outnumbers everybody else, right? So now we've got
Yeah.
like 10, and we're starting to grow the physics program, which is what we're trying to do. So but obviously interested in this, and we're using the multi-wavelength universe on the gang of 5 at least.
Yeah, that's great. Hopefully these curricula will help. And take Daryl Jansen. And this happened to me when I first started the curriculum. My enrollments grew by 100% over 5 years. Daryl Jansen using OPIS and MWU and his own stuff, because he's probably going to spearhead the curriculum for the Argus curriculum. He's grown his program from 400. These are survey level students taking intro courses, 400 per year to 1,250 per year.
Wow. Now our survey uptake is much larger than that, by the way. Our survey uptake every semester is more along the lines of, capacity is somewhere like between 120 and 150 a semester. And so we usually fill up on the survey classes. So
And if you give them a good experience, you can steal some of them, turn them into majors.
it's the idea.
Yeah.
That was exactly why offering the astronomy concentration for physics, was created, because they felt it was like a good gateway to get people into the physics program. So,
And Opus and MWU, I used to think of them as, you start with Opus, then you go to MWU, but I really see them as orthogonal curricula. You could offer both at the survey level, I think. Opus is a little bit more cookbooky. We tell you exactly what you need to do. So it's more comfortable for many students. MWU is more artistic. They're going to learn how to make pretty pictures, but at the same time, then we get really physicsy on those pictures and start doing calculations and things. So it's a very different hook. It's not web assigned. They're going to be, they create blog entries, and so they learn a lot about writing. And a lot of the research, and I know it sounds like a stereotype, but a lot of the research shows that guys tend to gravitate more towards the physicsy, mathy stuff, and girls more towards the visual stuff. And so this may be an entry for women, an easier entry for women into the sciences.
So we're actually, what we're looking at, we had a meeting about this, our curriculum. So obviously the survey, which we're going to base on OPIS, that's going to be a key part of it, to get it more experiential, right?
Mm-hmm.
And so since we mixed the lab and the class anyway, and then there's a follow-on class that originally we were going to do for just majors. We were talking about do multi-wavelength universe, but we're also pitching that as astrophotography, and so that, and we're making it so that you can open that up to get more people in, instead of just saying, oh, you got to take the 101 and you've got to be a physics major to do it. So it's real interesting you mentioned that, because we were just having that discussion last week.
I think it will work in the sense that, where Opus is more individual, maybe you're working with someone, but you're really doing it yourself, presenting it yourself. MW is teamwork. And a key thing is building teams. So if it's a mixture of majors and non-majors, you want to do like a skills assessment early on. You're going to want, and maybe it's just self-reporting. Maybe this person says, I'm into the astrophotography. Someone says, I'm into the physical calculation. And someone says, I'm into writing and presenting, science in that format. Or I'm really technologically capable. And then you want to form a team. So yeah, you may have some non-STEM people in there, but they bring critical skills. What you don't want is to have all your physicsy people in one group, all your artsy people in another group. But if you can effectively mix the groups, I think it will work.
And we're talking about doing some strategies like that, again, it gives more on-ramps into someone who really decides they're into it and they want to stick with it, right? So,
yeah. Mm-hmm.
I mean, we've got growing enrollment. And so we're trying to take advantage of, as the school in general has growing enrollment. So, and we're improving our retention from year to year, and so like we're kind of in a good position to like we're getting more candidates. So it's like I want to try to bring as many in as we can, right?
Yeah, it's nice that you to be part of a growing program and have a lot of control over how to make it grow and the direction in which it grows. So you strike me as happy doing what you're doing.
Actually, yeah, again, if I were at UNC, I mean, obviously I'd be helping out, and doing things like that. But yeah, I certainly, yeah, I would probably would not have the degree of freedom that I have at a smaller school, right? Being a smaller guy, like so obviously, you guys are doing great things. Don't get me wrong, it'd be fantastic. But at the same time, it's like it's kind of nice because we have a small school, a smaller school. Although we're approaching 11,000 undergraduates, so we're getting there. But it's good to have that kind of control and be able to do some of these experiments and get a lot of support for that. So that's actually a good thing.
Here, our Astro group gets, the harder it is to achieve consensus, the harder it is to move from this to that. And
Right.
so it becomes more of a struggle where you can just say, let's do this, and it gets done. I'm envious of that.
I
And
teach in the computer science side as well, and there's a little more of that because it's a larger department, more established program, and it's like, yeah, sometimes I do have some flexibility there, but changes are it's a little different experience than, well, what do we want to do in astronomy? Like,
you mentioned this, and the Argus curriculum will have a programming component to it. We're going to build these GUI interfaces, but we're going to hopefully do it in such a way that you can plug in different algorithms, and the students can code things and try different things. So it really is a more advanced thing, but it will touch on comp sci.
but it's critical to do that.
Mhm.
And one of the reasons I help out in computer science is that we're just getting bombarded by all kinds of majors
Mhm.
taking the intro to programming classes. I mean, I'm course coordinator for those, and I mean, we got like 13 or 14 sections I'm coordinating over multiple instructors because it's just like the demand is just huge, right?
And astronomy is such a great application, at least for data science, which is just a part of computer science. But
Right, yeah, but I mean, just knowing the basics. They want to know the
Mhm.
basics of Python is what we teach in intro.
Yeah.
So like they all want to know that because they're all like, yeah, like the math majors want it. Like we even branched off a couple of specific sections in math that don't even count in that count I had, and I gave them the material for that because they want to do a mathy version of it, but it's still like, it's yeah, more and more.
And I'm
So
really excited about Argus's possibilities here, because if you're interested in data science, it doesn't get bigger.
yeah,
Netflix has it beat by a little bit. Netflix worldwide streaming, but there are few data sets that are bigger and faster growing than what Argus will be, and it should be ready in 3 or 4 years.
yeah, it's incredible. It's an incredible project, but it's also really interesting from the data side, just having to be able to manage all that.
Yeah,
It's no longer you get a little bit of data and then you send some graduate students off to work with it, right? It's like, you're getting your hard drives full of data, and it's like,
yeah.
yeah,
We're running through some of the possible things students can do using like sparse data from VSX, from AVSO, and some other things like Assassin, but the data set's going to just be can you know you for dense throughout the night, not a few random points here and a few random
right,
points
yeah.
next night.
Yeah, there's not like an easy high order sort you can put through to just say, okay, here's just the few interesting things. It's going to be like, yeah, it's all interesting stuff, right?
Yeah, it's not like trying to tease, okay, I think this is going on physically in this crappy merged data set from all sorts of different sources with each with their own system X. It's just going to be overwhelmingly clear in most cases what's going on and new. stuff that no one's done before. Everyone can just pick their own object and master it and then submit
Right,
it.
yeah. Look at someplace, say, I want to look at that, you know, and
Mhm.
so just real quick on the math, the example math, I was going to do some for 4 and 5. If you haven't done that, so do you want me to send you what I have,
Yeah,
sample calculations?
Yeah, that'd be great.
Okay,
That'd be great. And
I've got some students asking for some
use
help. So,
them, or adapt them, and wonderful.
yeah, I'll just, yeah, create something simple. All right, hey, Dan, thank you so much. Well, have a good couple of weeks.
You too. Have a
All right,
good
bye.
end of the semester.
Thanks.